Alright, so geometric sequences and series. Geometric sequences first. Okay. So let's start with an example of a geometric sequence. That would be, okay, how about this? That would be 1, 2, 4, 8, 16, 32, 64, and so forth. And so we know this is a geometric sequence because 1 times 2 is 2, and 2 times 2 is 4, and 4 times 2 is 8, and so forth. So in this scenario, 1 is the first term, and 2 is the rate. And, well, oh wait, here's a comparison. Arithmetic sequences are to arithmetic series what geometric sequences are to geometric series. So basically, if we want to find the geometric series of this sequence, that would just be 1 plus 2 plus 4 plus 8 plus 16, so forth. So this is an example of a geometric sequence, and this is an example of a geometric series. And so, okay, and our first problem for today, problem 6, is a proof actually. So we want to prove that a plus ar plus ar squared, comma, plus, all the way up to ar to the n minus first power. And we want to prove that's equal to a minus ar to the nth power divided by 1 minus r. Alright, well, what you notice about this portion here first is that it's a geometric series. So we start with a, which is the first term, and the second term is equal to a times the rate. So, back to the first example we had, if we had 1, 2, 4, 8, and so forth, a would be 1, and r would be 2. And, well, we want to find an easier way to find the geometric series, just like we found an easier way to find the arithmetic series. And so this is the formula for it, but we have to prove this formula first before we can use it. So I'm going to label this S. S is equal to the geometric series, a plus ar plus ar squared plus, and so forth, plus ar to n minus first. And I'm going to make another equation, and I'm going to multiply s by r. So SR, well, that's equal to, well, we multiply each of these terms by r, right? So that's equal to SR is equal to AR plus AR squared plus AR to third power plus, and so forth. And we know the last term is AR to the nth power because we're multiplying another r to this problem, to this term here. Alright, so now what we can do is subtract. I'm going to subtract upwards, if that makes sense. Or I can subtract downwards actually. Now I'm going to subtract upwards. So I'm going to multiply all these terms by negative. So this is negative, and this is negative a, and negative ar, and negative ar squared, negative ar to the nth term, and then I'm going to add these together. So what I get is SR minus S is equal to, well, this is the part where things get interesting, because we have a negative a here, right? So it's equal to negative a, but positive AR minus AR is equal to 0. So we can kind of get rid of this. That's a 0. And then positive AR squared minus AR squared is also equal to 0. So we can ignore this part. And then we can do this so forth with all the terms in between until we reach this part here. And this part here, well, before AR to the nth power, we also have AR to n minus 1 power. And this is positive, this is negative, this also becomes a 1. So what we have left is negative a plus ar to the nth power. And then we can simplify this. So here, let me rewrite this part as ar to the nth power minus a. Well, do you remember what we learned about factoring last week? We can factor out the s in this part, so it's equal to s times r minus 1, and that's equal to a times r to the nth minus 1. And then s is just equal to a times r to the nth minus 1 divided by r minus 1. R to the nth, yeah. And well, this is actually equal to this part over there. I mean, the numbers are a little bit flipped, but here we can turn this into ar to the nth minus a, like I'm going to just distribute it. Then we have r minus 1. But if we multiply the top and the bottom by negative 1, and that still makes the fraction equal, we get a minus ar to the nth divided by 1 minus r. So we get this format here. But these two are basically equivalent. And that's how our proof goes. I would say this about the geometric series proof. It's much easier to remember the proof than it is to remember this. So if you ever like forget this formula here, just remember how we did the proof. Okay, problem 7. And we're actually going to use this formula now in a problem. So problem 7, evaluate 2 minus 2/3 plus 2/9 minus 2/27 plus 2/81. Okay, I'm going to write that out. So our first term, our a, is 2. We want to subtract 2/3, then add 2/9, subtract 2/27, and add 2/81. So to get from 2 to negative 2/3, we multiply by negative 1/3. And we can see this holds true here. Negative 2/3 times negative 1/3 is equal to 2/9. And then so forth. So we know what for all the variables in this formula here, we can solve for them, right? We know what a is and we know what r is. A is 2. R is negative 1/3. The rate is negative 1/3. And n, the number of terms, well, we can just count, right? 1, 2, 3, 4, 5. We have 5 terms. So if we just plug into the formula, we'll find our result without, adding up all of these fractions. So a, 2 minus 2 times r to the nth, negative 1/3 to the 5th power, divided by 1 minus r, so 1 minus negative 1/3. Okay, I'm going to use a calculator for this one because simplifying it will take some time. So 2 minus 2 times negative 1/3 to the 5th power divided by 1 minus negative 1/3. 2 minus. Okay, and that is equal to 122 over 81, which, yeah, it seems like a reasonable amount. I'm just thinking. So 122, okay, normally we want to leave our answers as an improper fraction, right? But that is also equivalent to around 1.5. So yeah, it makes sense. You have your large number 2, you subtract roughly 1/2, and then these numbers are kind of insignificantly small, so they won't impact it all too much. though we do added 2 9s, which must have boosted this up to 1.5. Anyways, that's problem 7. Let's go on to problem 8. So the thing is, the formula we just learned here is called the formula for there's infinite geometric series and non-infinite geometric series, limited geometric series. So you notice that like this geometric series ends, right? But the interesting thing is sometimes an infinite geometric series can have a sum. So for example, let's say that our infinite geometric series, the rate of our infinite geometric series is 1/2. So we start with 1/2, right? We start with 1/2. And then the second term will add on 1/4 to it. And then the next term will add on 1/8 to it. And the next term 1/16. Oh, that should be smaller, but oh well. 1/16. And then 132, and then 164. But the funny thing about this problem is that even though we're adding more and more terms, we're never going to reach bigger numbers, like for example 10. This thing is never going to add up to 10. And that's because this infinite geometric series actually has a finite sum. And so our formula is to prove that a plus ar plus ar squared plus ar to the third power and so forth is equal to a divided by 1 minus r. And so I have a warning about this problem. R has to be a fraction. Like it has to be a fractional number. It could be negative and it could be positive, but it has to be a fractional number because each term has to be, well, decreasing, if that makes sense. For example, in this finite geometric series, the sum just increases and increases and increases and increases, and it never levels off, right? So the more terms you add, just keep on increasing. But with this infinite geometric series, there's actually a sum to it. Like it has to end at some point, and adding more terms will just get it closer to that sum. So just remember, if you're trying to find the geometric series for an infinite geometric series, r has to be a fractional, and this is the formula for it. And we're going to prove this the same way we proved this problem here, problem 6, I believe. So s is equal to a plus ar squared plus ar to the third power and so forth. SR is equal to ar plus ar squared plus ar to the third power and so forth. And so this proof is a little bit more elegant. Actually, this formula is also more elegant than what we have up here because if we subtract it, actually let's subtract downwards this time. So s minus sr is equal to a. This becomes a 1 and 1, 1 and so forth, right? This becomes 0 and 0 and so forth, right? So s minus sr is just equal to a, because this goes on infinitely. So these will all these terms will cancel each other out and leaving only the a, and then we can factor it. So s times 1 minus r is equal to a. S is equal to a divided by 1 minus r. And that's how we proved that s is equal to a minus r up there. Alright, so we're going to solve problem 9. Oh man, that one's pretty tricky if you don't know this formula here. a divided by 1 minus r. So problem 9 has an infinite geometric series. We have 1 plus x squared plus x to the third power plus x to the fourth, so on, and we want to find, and it's equal to 4, and we want to find what x is. Well, first of all, what's your a term? Your a is equal to 1. That's the first term here. And your x, not your x, but your rate, so from here to here, and from here to here, and from here to here, well, you multiply by x each time. So r is actually equal to x. And so the problem you want to solve is 1 divided by 1 minus x is equal to 4. So, right, so the geometric sum of this series here is equal to 1 divided by 1 minus x. We know that the actual number is 4. So now what we want to figure out is what x is. Well, we can just, we can do what we learned before for solving systems of equations. So we multiply both sides by 1 minus x, so 1 is equal to 4 times 1 minus x. And I'm going to distribute this so that we have 4 minus 4x. And then I'm going to add 4x to both sides and subtract 1. So we get 4x is equal to 3. And then we divide by 4 on both sides and we get x is equal to 3/4. Wait, did I do that? Right. That's 3, yeah. So we get x is equal to 3/4. And that's, coincidentally, what we want to find. What value of x makes this true? Alright, problem 10, geometric means. Okay. So one thing we've been trying to emphasize when we're doing these problems, sequences and series, is that there is always a difference or a rate that makes a series or sequence what it is. So for geometric sequences, there's always a rate. And that rate comes in handy when it comes to talking about geometric means. So for example, back to our first example, 1, 2, 4, 8, 16. And our rate is 2, of course. So we start with 1, and then our next term is just 1 times 2. And our next term is 1 times 2 squared. And our next term is 1 times 2 to the third power, and so on. But if we're trying to find a geometric mean, you might notice that if we take the square root of this number here times this number here, we end up at this number. So that's 2 times 8 square root of 16, which is equal to 4. And that's, coincidentally, what this number is here. So the thing about geometric mean is that any term is always the geometric mean of the two terms that's to its left and is to its right in a geometric sequence. And so now you have problems like this that states that to insert two geometric means between 3 and 4. So we have 3, we have one geometric mean, and then another geometric mean, and then 4. And we want to figure out what x and y is in this problem. So what we can do is to remember there's a rate. So 3 times r is equal to x, and x times r is equal to y, and y times r is equal to 4. So we can redefine x in terms of 3 and r. So x is equal to 3r, and y is equal to x times r, which is equal to 3 times r squared. And 4 is equal to y times r, or 3r to third power. And so this equation here is the most important for figuring out what r is. We know that 4 is equal to 3r to the third power. Well, we divide by 3 on both sides, 4/3 is equal to r to the third power. Then we take the cube root, so r is equal to cube root of 4/3. And so for this step, I would advise you not to simplify this yet, just leave it as this. And you can't simplify it, I believe. You can't, yeah. So if we want to figure out what x is, well, x, back to this equation, we know what r is, so we know that x is equal to 3 times the cube root of 4/3. And y is equal to 3 times cube root of 4/3 to the second power. And okay, you guys will become more comfortable with simplifying radicals like these moving forward. Here, let me erase some of this work, and then I'll simplify these two. I believe that you can leave x just as it is. Oh, little papers. Yeah, you can leave x just as it is, as 3 times the cube root of 4/3. Then for y, well, if you square it, that's also equal to 3 times the cube root of 4/3 times the cube root of 4/3. And so when you multiply these two together, you get 3 times the cube root of 16/9. And I believe you can't simplify this even further. Here, I'll check. Cube root of 4/3 squared. Oh. One 1.21. Yeah, this is the furthest you can get in terms of simplifying these problems. So yeah, we figured out what x and y is. X is equal to 3 times the cube root of 4/3, and y is equal to 3 times the cube root of 16/9. These numbers are a bit messy, I admit. So I would say you cannot guess and check these problems. You have to understand what geometric mean is. You have to figure out that there is a rate between them. So just keep these things in mind. You don't have to memorize any of the formulas. For geometric series, for arithmetic series, you don't need to remember them. Just memorize the proof. And during competition, hopefully you can quickly write out the proof for those formulas. I wouldn't recommend that you spend too much time actually memorizing these formulas without understanding how we got to those formulas. Anyways, thank you guys for watching. I'll see you guys next week.